completely analogous to deterministic theory. You just have an expectation. Cool. Shall we play some more? Why would I write it something like this? I'm giving it a funky name just to make sure I'm not giving everything away. Given the analysis we just did with this funky thing, do you think anything special will happen with this guy? Any ideas on what this thing means to me? It is a solution of Poisson's equation. Provided, of course, so V3 holds, so I can get a handle on things like this. It's unichain. Or X dot, forget it, this X dot irreducible. And C of x is less than or equal to a constant times f of x for all x. And I really should make that clear. I've been saying I need my cost function bounded by f of x, and f is positive. Sorry. I can always scale everything up. Okay, so don't worry about c being less than f. C could be less than 100f. Or whatever, So under those conditions. And so the proof, now that we have this pretty lemma, the proof is a one-liner. I think. Let's check it out. Maybe not a one-liner. Funky things happen. We'll have two cases as before. So we know that if I hit p psi of x, I've got to go through all this work again, do I? It's going to be that. Instead of summing from 0 to sigma, I'm going to be summing from 1 to tau. All right, so the same arguments from here to here to here to here to here to here. I'm going to get this. Okay. Not S. Okay, so let's look at the two cases. So if x is not equal to the target state, right? If x is not equal to the target state, then sigma and tau are the same thing. So therefore, I'm summing from 1 to sigma. It's exactly the thing I started with minus the first term. Yeah, so again, sigma s equals tau s if x0 is not in S. That's the thing I'm using over and over again. For any set S, in this time S is a singleton. Just look at the definitions. You know, if x0 is not in S, then k equals 0 can be ignored. Right, cool. So if if tau equals sigma, I get exactly the same sum, but I lose the first term, so I get psi of x minus c tilde of x, and that deserves a happy face. You know? That looks like Poisson's equation. But what happens in x equals x dot?
You don't give a solution.
We'll take a look. What happens? Who knows what the hell that is? What if x equals x dot, everybody? I heard it. What, say that again? No, this is tau. So we're delayed. So tau s is the return time. Yeah. So you've got to go back to Keck's theorem.
Is it going to be 1 over x dot?
Yeah.
I mean, what, pi of x dot?
Yeah, pi of c tilde. Oh. Which is 0. You see, that's Keck's theorem. I know it looks a little different. So Keck's theorem said that, well, 0, which is pi of c tilde, right, is equal to pi of x dot times the expectation starting at x dot, which is what I'm talking about. X equals x dot. I'm sticking x equals x dot here. And I go times the sum k equals 0 to tau x dot minus 1 of c tilde of xk, right? So I know the sum from 0 to x dot minus 1 is 0, right? And here I've got a sum from 1 to x dot. It's all messed up. Anybody tell me how I can fix that? So remember, we're starting at x dot here. So that's why the first hit we get a c tilde of x dot. Here we're ending at x dot. So we get a c tilde of x dot at the end.
Shift.
It's exactly the same thing. It's just basically that last term here is the same as the first term here. They're identical. It's accounting. Each one of these sums has exactly one c tilde of x dot. And here it's at the end. And here it's at the beginning, because we started at x dot. So it's 0. Okay, so that's why that's 0. Happy face. And now, is that a happy face? Well, what is psi of x dot? What is it? What's psi of x dot? C tilde of x dot. So 0 is equal to psi of x dot minus c tilde of x dot. So there it is. So there it is. So there's a proof and there's a QED. And so this representation is really useful because you can try to estimate this thing through generative cycles, while the other representation involving infinite sum you can't. And also, this is always true. So under V3, H exists and has this form. The other representation I showed you is not true. It's not meaningful. So this is a more general and useful representation of Poisson's equation. All right. Cool. You all happy? And you could have, I mean, let's just play around with one more trick. So this lemma was everything, right? The converse theorem, the representation, yeah, this was it. You could have guessed this representation from other means.
So you need the x dot irreducible condition because pi of x dot needs to be greater than 0. Right?
No, right there, I want this to be 0. I want to be able to represent pi in terms of cycles, regenerative cycles. So it's right there.
And so pi of x dot will always be positive. Right?
Oh yeah, I mean, but yeah, sure.
Yeah.
Oh yeah, absolutely. But I mean, there's no, yeah, sure. But I mean, if this was 0, then pi would be 0. That wouldn't make any sense. Yeah. So, yeah.
Could you explain
Yeah.
the psi of x dot minus c tilde
Oh, no,
something again?
right there. So if you put in x equals x dot, so take, oh, I've erased it. Remember, sigma was the first time, including 0, that I visited the state x dot. So if I started x dot, I immediately stop. You're already there. So what's the sum from 0 to 0 of c tilde of x?
Just c tilde.
Of x0. But x0 is x dot.
Okay,
Yeah.
so it's 0.
Yeah. So yeah, so psi of x dot is exactly c tilde of x dot. Yeah. So the way in which you could have guessed, another way you could have guessed this is that if you look at the same tricks we looked at before, if I define mn to be h of xn and then plus if I define this for all n greater or equal to 1, and at 0, it's just h, then what kind of process is mn? Something that horses use in England? It's not super, it's only ordinary. It's a martingale. It turns out if you look at the expectation of mn given fn minus 1, just like before, this is already in the past.
It's a weak martingale.
Yes, it's called a martingale. No, but I mean, beta martingale is much stronger than beta super martingale. There's no... just like all of us ordinary people are much better than super people. And so this, by Poisson's equation, is just equal to h of xn minus 1 minus c tilde of xn minus 1. That is Poisson's equation. All right. And so if you crossed your fingers, you might hope right? So I'm not saying this solution to Poisson's equation. I'm saying suppose somebody handed me a solution to Poisson's equation, and then I decide to plug in a random time here. I might hope this is true. Well, it turns out, as you will see, this is often true. And so then, what is this? It's just this. All right. Now, that's not a very useful identity unless I do something to make that deterministic. If I want a representation of H, this is not a representation, but a fixed point equation. You know, we started out with dH equals minus C tilde. You know, that's some sort of a linear equation for H, right? And so this is another linear fixed point equation. But if you choose tau so this is deterministic, this becomes just a number. And the solution of this equation is not unique anyway. I can always add a constant into the solution. Do you remember that? You know, this is saying that pH equals H minus C tilde. I can add any constant to both sides. So the solution of this equation is not unique. So the trick here is to choose tau to be tau x dot or sigma x dot or whatever. But tau x dot would work as well. Or you could put in the 10th time I visited x dot. Anything that makes this deterministic will work. All right. So choose tau. So we did it there, sigma x dot. Again, only because we did it there. And so then what you get is exactly what I said. You get that h of x is equal to, what's that? It's sigma x dot. That's a time at which I visited x dot. So it's just h of x dot. There's a little x there. Or sigma. Oh, there's a minus 1 there. Yeah, let's put it in. Because the minus 1 is going to kill us, right? So let's make it, let's do that. But that's not right. I cheated. There's a tau minus 1 there and a sigma x dot there. What am I going to do? How can I fix that? I've got one extra term here. I said, let's take tau equals x sigma dot. Here I'm summing to tau minus 1. Here I'm summing to sigma. How do I fix that?
Add and subtract a term.
Thank you. So I can always kill it off. The very last term is just, I'm plugging in x at sigma x dot. Well, that's just that. So I can kill it off. And then I get a minus 1. Yeah. Crazy, I know. But actually, this is a horrible choice because it can be 0. So you know, it would be much cleverer to choose tau x dot or something else instead. But this is all valid. So so yeah, you can justify these steps, and it turns out that's another way of getting at this. But justifying this is really damned hard. Well, justifying this is one trivial lemma. All right. Okay, cool. So that's it. So we did the converse theorem, we did the representation theorem, which I feel will be really valuable. And now we're going to stop that. I can talk about coupling and its implications, and then that way next week we can get into dynamic programming. Okay, but now we should have a break because we're going to have a new topic for the rest of the hour. That's Jarvis. Yeah.
So, is there a special significance to the expectation of n tau being equal to the expectation of n0 with respect to x?
No, I'm saying that we can hope this. I mean, given that I could take expectation. I mean, it's basically I'm going back to the last lecture where we had inequality.
No, yeah. So, but what is there a property?
Where?
Is it called a special thing?
No, I mean this.
Yeah, the expectation being.
Well, this is true if tau is bounded in some sense. It's a, yeah, I mean, yeah. Well, it's an optimal. There's an optimal sampling theorem, but it requires conditions. Yeah, and that's why I can't really prove it. That's why I'm just saying that you could guess this representation just by fooling around like this. That's all I'm trying to say. There's no theorem here. Well, this is a hope. This is a reality. There's a derivation. And in fact, I should say, this is where there's a lot of errors in the research literature, because they assume this. So there are papers in Markov on optimal control where they go through these steps and they make this conclusion, and it's completely false. And you know why? Because there are solutions to pH equals H minus C plus eta times 10 to the 10th. So there are solutions to this linear equation where you get completely the wrong constant, and H turns out to have massive growth, and so all these steps are not valid. It's just not true. So there's a big paper that's very well cited on conditions for the existence of optimal policies for MDPs. So conclusion's completely false, because they forgot that you can't just do this. Yeah. So if I find a state space, you just go through and do it. But these are like countable general state spaces. So if you want to, I'll give you an example of that. I mean, it's not hard to generate them. Yeah. So I should put that as a little bad check. That's not a solution to Poisson's equation, because when you solve Poisson's equation, the constant has got to be the steady state mean, and in general it can be bigger, or maybe well, for positive C this could be bigger. Yeah. All right, take a 5-minute break. All right. Yeah. Sure.
The equation with C tilde,
Yeah.
the solution for that was because that's why we introduced like the mean subtraction.
Well,
was to get
Oh, no, the solution of Poisson's equation?
Subtract off eta, then any solution of that would be.
Well, I mean, H is not unique.
H
No.
for that is not unique?
Oh, no, I mean, surely not. Like I said, you could add a constant on both sides. Like add 1, you know? So if I let g of x be equal to h of x plus 1, right? Then what's going to happen when I hit g by p, you know? I mean, the conditional expectation of 1 is just 1.
Yeah, sure.
So pg is just equal to hph plus 1. And what's pH? It's h minus c tilde. But what's h plus 1? It's g. Yeah. So it's very much like eigenvectors, you know, where they're, you know, but here it's different. Eigenvectors are only unique up to scaling. Here it's unique up to additive constant. So I take it back. It's not like eigenvectors, but yeah.
So remember originally it was like pH equals h minus c plus a to the power, but then
I mean, this is c tilde. That's what c tilde of x
it's just a
equals c of x minus pi of c.
yeah.
And you do that so you can get it. I mean, in a finite state space model, you can't solve this unless you normalize. There's no solution. I mean, you can see why. I mean, to hit both sides by pi. Remember, pi p equals pi. Yeah. So in a finite state space, hit both sides by pi. You know, pi p. Pi. These guys are the same. Yeah.
Could you repeat the last thing? So you hit both sides by pi?
Are we starting up again? Oh yeah.
It's on because last time
Oh yeah. Good. Thank you. Now there was a question about uniqueness. I mean, just to make sure you all know. And actually, let's just stick to a finite state space. Otherwise, I can get into these tricky, you know, subtleties. So, fact number 1: the solution's not unique. And here's an example. If I solved it for 1h, I could just add a constant, like 1. And if I hit g by p, remember there's a conditional expectation, and the conditional expectation of a constant is the constant. So pg is ph plus 1. And ph is h minus c tilde, and 1 is 1. So you can see that g is also a solution to Poisson's equation. All right. Okay, and then, and it's basically, yeah, I mean, using the fact that d times 1, which is equal to p minus I times 1 equals 0, that's all. I mean, using the fact that, you know, we're talking about the, you know, p minus I here, p minus I. That's the reason for the lack of uniqueness. And the second thing is, why do I normalize? Well, I normalize in the finite state space setting. It's completely clear because I can hit both sides of this equation by pi. You know, and pi ph is pi h. Now, you could say, well, that's obvious. But I'm saying it's not obvious. We normalized it so we could solve this equation. All I'm saying is that if we don't impose the condition that pi of c tilde is 0, we cannot solve this equation, all right, on a finite state space. And so on a countable state space, horrible things can happen, you know. You can solve it even though this is huge, you know. I'll let you do it. Try, you know, try the MM1Q again. H of x equals rho to the minus x, and hit that by p, you'll get something horrible. You're going to get ph equals h minus c tilde in quotes, and pi of c tilde will definitely not be equal to 0. So basically I'm inverting the invariant measure. You know, the invariant measure is geometric. You know? So this is something that blows up way too fast. In particular, remember pi of x is 1 minus rho times rho to the x. So this is chosen so it doesn't have a finite mean. You know, pi of h is 1 minus rho times this, times the sum x equals 0 to infinity of rho to the x times rho to the minus x. That looks like infinity to me. All right. But yeah, but if you actually go through and do this, you'll see it. You get gobbledygook. So you got to be careful. You think you have a tight bound, you don't. That's all. Yeah. And these actually lead to real mistakes in literature. So cool. So again, I'm making my caveat, or my defense. There's not a single thing I'm presenting in this course that I don't think is valuable if you're going to do some research in any of these areas. If you're, and even if you're not, even if you're just going to go and write code, you want to know why it doesn't work, right? And you're going to want to do simulations to play around with things. And so this next topic about coupling is a way to understand simulation and so forth, as well as being an analytical trick. So I'm really not just trying to force feed you mathematics. So right now, today, in the remaining 45 minutes or so, I think I could even maybe do this. At least I can explain what coupling is. It's so easy to then apply that to prove convergence of value iteration. I might even try to sneak it in. We'll probably have to wait till next time. Okay, so value iteration is an approach in control for estimating, computing value functions, and it's really convenient to explain it first in the non-controlled setting. So what is coupling about? You see, one of the reasons I like it is because it illustrates there are so many ways to think about a realization of a Markov chain. Okay, so what basically the idea Okay, so we have our Markov chain, and we have another Markov chain that's better understood, and we want to create a probability space, create a simulation environment, if you like. We're going to write computer code so that these guys actually become the same thing. So basically, we construct all right. So what's an example of being better understood? Well, one might be that it's stationary. All right. And so then you can go through and look at the expectation of C of x of t, which we don't understand, right? We've got our Markov chain. It's starting off in Never Never Land, far from being stationary. And I can look at the difference of that and its steady state mean. So this is the sort of thing that we analyzed using spectral theory before. Right? We said that if the eigenvalue is blah, 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 then this would go to 0 geometrically fast. So we can still say that in a finite state space. But more generally, we can look at this and we can say, well, that's equal to this. Right? Now I did two steps here, okay? I used the fact that expectation is linear, so the expectation of the difference, is the difference of the expectations. And then I used the fact that I just said that the mean of C of y of t doesn't depend on time. Okay, so that's just pi of c. Right? Now, these guys are equal. So the difference is 0. That's awesome. There. All right. So basically, if you can construct a coupling time for which, that's almost surely finite. So if you can construct a time for which this is true, then we've proved the ergodic theorem, say, for bounded functions, right? Because if c is bounded, we just look at the probability that tau is bigger than t, and that goes to 0 as t goes to infinity.
Did you just forget to write the expected value for that C of y of t right there?
Where? No. It's there.